to everyone. This is Ashok Kumar from Construction Management Training Institute from Bangalore. Today we are having a program webinar on the upcoming topic is on the self-compacting concrete. It is the need for our and a lot of transformation is happening in the industry towards the digital construction and advanced construction. So in this context, I invited Dr. Jagdish for this nice topic. He has immediately accepted and he has given his consent and he is giving his time and experience to you guys. In this pandemic, you can utilize your time to learning to take the learning on the advanced materials and advanced the process and the technology. Last week we conducted a program on formwork, which is aluminium formwork with Mr. Dr. Raghavendra Holla, and the next program is on concrete. Yes, of course, it will be required. Both are required for the construction. And Dr. Jagdish, welcome to this program. And about your profile, I invite Janani. Janani, can you read sir's profile? He is having an excellent experience in the academics and in the, he's having so many roles in the as a startup advisor. A lot of things sir is doing. It's an elaborate profile. We would introduce sir's profile to you, and you can take the learnings from him about the advanced technology. Definitely, I hope this webinar will be useful for you. We are conducting so many webinars, nearly 70 plus we have crossed, and this is one of the innovative topic which we have not touched. So I invited Dr. Jagdish. Sir, welcome to this program. And I request audience to mute your mics. If anything support required, you can use the chat box anyway. Our people will help you. Janani, please.
Yes, sir.
Yeah.
Can I share my screen, sir?
Yeah.
Okay, sir. Is my screen visible, sir?
Yes, please proceed.
Yes. Good afternoon to all. This is Janani. I'm a final year student at SSN College of Engineering, Chennai, and I'm currently an intern at Prayojana CMTI. I take immense pleasure in inviting and welcoming the guest for today, Dr. Jagdish Vengala. Dr. Jagdish Vengala obtained his master's degree in construction technology from BMS College of Engineering, Bangalore in 2002, and his doctoral degree on seismic response of study of bamboo-based constructions from VTU Belgaum during 2015, for which he was conferred with INAE Innovative PhD thesis by the Indian National Academy of Engineering. He was also the recipient of Professor V. Ramakrishnan Young Scientist Award for the year 2008-2009 by Indian Concrete Institute and the 5th CIDC Vishwakarma Award under the category of Achievement Award for Scientists for the year 2013. He has guided more than 25 MTech and BTech students and has got more than 20 years of research, industry, and teaching experience. His research interests include self-compacting concrete, concrete technology, cementitious materials, earthquake engineering, bamboo-based and prefabricated housing and building materials. He is currently the head of EDC Innovation and Incubation Center and also the Associate Professor, Department of Civil Engineering, PVT SIT, Vijayawada, Andhra Pradesh. We welcome you, sir.
Thank you,
Janani.
Thank you.
Thank you, Ashok Kumar ji.
Thank you, sir.
And maybe I'll start my presentation.
Sure, sir. Please. Before a presentation, I would like to request audience, you can pin Dr. Jagdish Vengala presentation will be there in your the people's list. There will be 2 names will be there, and you have to pin the presentation. If you have any difficulty, you can use the chat box. That will be better. Thank you.
Yeah, good afternoon, one and all. Thank you, CMTI, for inviting me to deliver a talk on self-compacting concrete as a part of knowledge sharing session, which the Institute is contributing a lot. And thank you, Janani, for introducing me. So let me get into quickly the topic, self-compacting concrete, which I have worked, believe it me or not, 20 years back. So I started my work on self-compacting concrete 20 years back in 2001. Anyway, I'll share the knowledge which I've gained, and over a period of time, the experience or the projects I have carried out on this topic. So there are a lot of students and teachers and maybe their professionals might be having. Maybe I'll go very slow and then slides quickly so that I can cover what I would like to cover for a period of 1 hour. My contents for this presentation are like this. I'll just give you a small brief about normal concrete, then how do you achieve flowable from normal, and then what is self-compacting concrete, what is the difference between flowable and self-compacting concrete, and why fresh properties of self-compacting concrete are important, and how do you accept this concrete, and what are the key insights in SCC, and some of the applications I'm going to present you, and also one mixed proportioning method, one or two methods. I'm going to give you some glimpses. And with then, how you can achieve with the different mineral admixtures, I'm going to present. This is a brief contents of my presentation. So let me start my presentation with a small video, which I have come across nearby my house. This is how the concrete is getting abused. Maybe I'll mute the video. Yeah. So this is how the concrete is getting abused most of the sites if you're not caring about the concrete. So manually produced site mix concrete, you can see there are a lot of problems. What is the problem in this video? I'll explain you. Here you could see the lady is putting coarse aggregate, sand, and you can see here just before dumping the concrete, the lady puts the concrete. I'll just slide it over. You can see here. Just now she has put the coarse aggregate and he has dumped the concrete. That means there is no proper mixing that happened. So you cannot just be left to the judgment or guesswork of this operator or a contractor. So this is the kind of manner concrete is getting used in many of the places. And it is very complicated to sense each and every variable. If it is changed, properties will affect it. You can see roadside, a lot of construction will be happening, particularly highways, the concrete laying, mixing, and few people, based on their awareness levels, the customers, particularly for bigger projects, they're going for either site-based batching plants or ready mix plants. So this is a famous table in IS 456. One has to know about it. So we'll concentrate on reinforced concrete. Here you can see, as per IS 456, the minimum cement content you can put it in the concrete for reinforced concrete is 300 kg per cubic meter of concrete. Suppose if you're making per cubic meter of concrete, the minimum cement content you have to maintain is 300 kg. And how do you design the mix? All of you know it is not based on grade, it is not based on water cement ratio, it is not based on cement. It is based on your exposure condition. This is very, very important. So IS divides exposure conditions into 5 categories. There is mild, moderate, severe, very severe, and extreme. So depending upon the type of exposure, the structure is going to be built. Based on that, you design concrete. Say you are going to, your structure is there in severe condition. You have to maintain the maximum water cement ratio is 0.45, minimum grade is M30, and you have to maintain a minimum cement content of 320. So to start with, you can design a mix by keeping these parameters into consideration. Similarly, for extreme conditions, you have to go for M40. Here, I would like to give a small example. If it is a mild weather, but you are building a structure, foundations which are buried under soil comes under moderate condition. And the structure above the ground level, that means the columns, beams that are exposed to the mild weather, comes under mild condition. What does that mean? Even though the weather is mild weather, the structural elements which are above the ground level are in mild exposure. The foundation, which is buried under aggressive soil or soil, comes under moderate condition. That means foundation, you have to design a concrete of a minimum grade M25, and the rest of the elements you can go for M20 or above. It depends on again the loads and other things. So anytime when you design a concrete mix, you design the mix based on the exposure condition. And IS permits the maximum cement to use in concrete per cubic meter of concrete, it is 450 kg. And you can see here, when you sum up the previous slide, the cement what you take for normal concrete is between 300 to 450 kgs. And a maximum of 0.55 water cement ratio you will take up, because to maintain the workability at the same time, minimize the void so that the reasonable dense concrete you get. And grade of concrete between M20 and M40. And IS permits the use of both mineral and chemical admixtures. The most widely used mineral admixtures we all know, fly ash, GGBS, and then for high strength concrete applications, silica fume and metacoulin and other mineral admixtures we use in a minimum quantities. Suppose if you take silica fume and metacoulin, we usually take between 5 to 15%. But in case of fly ash, we can go up to 30-35%. In case of GGBS, even one can go up to 60%. Anyway, I'll show the percentages about IS permits. So you make a normal concrete. Suppose if you mix water, or if you keep on adding more water to a particular mix, can you achieve a flowing concrete? Yes, it flows. But once, if you keep on adding the water, what happens? There are two problems you can get it. One is segregation, and another one is bleeding, because you don't have enough finer content to hold the water. So that by keep on adding the water, you may not get the flowing concrete. That means which is good workable concrete without segregation and bleeding. And if in the hardened state, what happens if you keep on adding the water? It leads to durability problems because the water gets evaporated and it leads air pockets, and the strength and other problems occur. So just to give you the difference between segregation and bleeding, segregation is separating out of all the constituents in the concrete, which results into non-uniform mix. That means the water cannot get holded by all the other constituents. Bleeding is generally a result of aggregate settlement, and the mixed water, that means cement water, it releases the excess water. It forms on the top, or sometimes it bleeds out. So these are the problems you will get if you are just adding the water to achieve flowable concrete. But anyway, you can achieve the flowing concrete by addition of chemical admixtures and by adding mineral admixtures to get the homogeneous mix. Now coming to the self-compacting concrete, the difference. So before explaining self-compacting concrete, I'll just give you some kind of overview of the chemical admixture importance. So for our country, if you take most common admixtures we use, plasticizers and superplasticizer, both we use. So plasticizers are usually water reducers, and superplasticizer, the name itself, high range water reducer. And we also use retarders and accelerators air entraining agents, purposefully create the air bubbles inside the concrete to accommodate the freeze and thaw situation. And for shotcreting and gunneting, you add some chemicals to hold the paste onto the reinforcement. So all these we call it as chemical admixtures. Not only superplasticizers, not only plasticizers, all these retarders, accelerators, everything comes under chemical admixtures. I'll just give you the concept of what chemical admixture, particularly plasticizer, does. When you add water to the cement, cement naturally flocculates. Flocculates in the sense all the particles come together. It forms a lump kind of thing. So in these lumps or flocks, mixed water get trapped within the flock. So if you burst the flock, what will happen? The water inside will come out. So this trapped water generally is not available for workability, but in the sense, you have to add some kind of admixture to release this trapped water so that workability will increase. So by adding admixture, that means plasticizing admixture, what it does, when you add the chemical admixture or plasticizer to the mix, the entrapped water is getting released and cement particles will move freely. Workability will increases. When workability increases, when you have more water available for the hydration, your hydration products also get improved. This is another picture. Just to mention once again, when you add water to the mix, the cement flocks will form. When you add the admixture, chemical admixture, it releases the trapped water and it becomes more workable. So what does normal plasticizers will do? It creates a different charges in the particles. So when cement particles having the same charge, when it releases, what happens? There is a repulsion that happens. So what chemical admixture does? It creates an interparticle repulsion, and thus the water gets released, the trapped water. So you can see the picture, bottom left-hand side. This is the picture of unflocculated, and this is the this is the flocculated, and after adding water mixture, this is how the cement particles. It's a microscopic representation. What actually this chemical admixture does by adding plasticizer, we do two things. We can achieve two things. We can increase the workability, at the same time you can increase the strength. How do we do that? Let us take a mix with 0.55 water cement ratio is giving a slump of 75 mm. It's a normal concrete and giving a strength of 51 MPa. When you add the plasticizer, what will happen? Without increasing the water cement ratio, it will increase the slump, okay, by achieving the same strength. 51, 50, it doesn't make any difference. So in the first case, by adding superplasticizer, you are getting more workable mix. That means the slump is increased. In the second case, you are actually reducing the water cement ratio and adding superplasticizer by maintaining the same slump. The first case slump and the third case slump is same, but by adding water, reducing admixture or superplasticizer, you are reducing the water cement ratio. Thus, you are getting more strength. You know that Abraham's law, water to cement ratio to strength. When water cement ratio increases, strength decreases. You are reducing the water cement ratio, and your strength is increasing by adding superplasticizer by maintaining the workability. So this is what the typical chemical admixture or a plasticizer or superplasticizer does. But when you look into the complex structures. Nowadays, mechanization, more complex structures, G plus 10, G plus 20, and 110 stories. So when you are designing, you have the complex reinforcement. And here I would like to give you one example. You cannot place the concrete from a particular, more than a particular height. We call it, they say 1.5 meters, free fall. You cannot throw concrete or place the concrete beyond 1.5 meters height. Okay. What happens, particularly this congested reinforcement, you are placing at a height, the concrete hits the reinforcement and it segregates. And mortar sticks to the reinforcement and coarse aggregate goes down if your mix is segregated or bleeded mix. If your mix is not good. So these are the problems that happens, particularly for the complex reinforcement situations. As I mentioned, flowable concrete I've showed, like by just adding water, you cannot get it. But to get a homogeneous mix, you have to incorporate more fines. Suppose if you have 100 particles, you have added water, there is an excess water available. If you add another 50 particles, these 50 particles will accommodate the excess water to get coated around it. So that means addition of or incorporating fines will reduce the bleeding or segregation, and it will enhance the cohesion of the mix. And flow enhancement can happen. But when you add excess, what will happen? It sticks or more cohesive. Again, the problem of placing. So you have to see that what should be your the workability of your particular mix. As I mentioned already, RMC and concrete pumping, they have advanced the methods, placing concrete, problems of compaction. These are problems are still remaining there in most of the sites. And current Indian scenario, if you see a lot of construction of large complex structures, particularly in fast track mode, is coming. So congested structural reinforcement, vibration is a problem. You take these cases, these pictures. That is, can you put or can you insert the vibrator, concrete vibrator, and vibrate the concrete? Why do you have to do the vibration of the concrete? When you place the concrete, there are small air pockets that are there. When you vibrate it, all the air pockets will come out and then you get a dense concrete. That is the purpose or significance of vibrating the concrete. But in case of congested structural reinforcement, there are a lot of problems. Even though you vibrate it, sometimes you cannot vibrate it in such situation. So these situations, self-compacting concrete is one such solution. What is it? It is a highly flowable concrete. It flows. Even it flows, it is stable at every place it flows. And it can spread readily into nooks and corners of the formwork. You have a bigger slab with a formwork. If you pour the SCC from one side, it flows and reaches the other corner with the same homogeneity, same stability, and it fills the formwork. You need not do any consolidation. You don't do any vibration. And at the same time, it will not undergo any kind of separation. That means when it flows or while flowing, the concrete will not get separated out. What does that mean? Suppose if it is flowing, there is a beam, because in this slab, a bigger slab, you have in between the beam reinforcement also. If a beam reinforcement come in between, so it has to pass through the beam reinforcement. So the aggregate should not, suppose what happens, if your mix is not good, all the aggregates will get stopped at this reinforcement and only mortar will go to the other side. What I mean to say is, if it is a good SCC, it is a flowable, stable concrete, it can readily place into, fills the formwork without doing any consolidation and without undergoing any significant separation. So where it started late 80s, 90s in Japanese construction industry, concrete industry. And the motivation behind the SEC is, in Japanese construction industry, there was a gradual reduction of skilled workers during that time. Because of the reduction of skilled workers, the reduction of quality of construction took place, particularly the concrete work. So this is the origin to come out with the SEC. There are a lot of advantages. It shortens the concreting period. It eliminates the noise due to vibration, minimize the voids, avoids the honeycombing, it eliminates the compaction. We'll see all that. Okay, let us see some of the characteristics of self-compacting concrete when compared with the normal concrete. Normal concrete, when it comes to cement content, cementitious content, it varies between 300 to 450. We have seen in the previous slide. But in case of self-compacting concrete, the minimum content, the minimum cementitious content or higher, the powder content starts with the 450 and it's between 450 to 600 kg per cubic meter of concrete. In case of normal concrete is 300 to 450. In case of normal concrete, if you take a typical mix of 1 to 4, I cannot say because all our design mixes we follow at the site. Say if you take a typical M20 grade of concrete, the coarse aggregate is approximately 1100, 1200 depending on the mix, and fine aggregate is around 700, 800 kgs. But in case of self-compacting concrete, you have a lower or equal coarse to fine aggregate ratio. What does that mean? Either last case I have told 1100 plus 800, around 1900 kgs of aggregate is there in a concrete out of 2400 kg. So in case of SCC, it is equal. What does that mean? Out of 1900, 850 is fine aggregate, 850 is coarse aggregate, something like that. So either equal or sometimes 700 is our coarse aggregate and 750 is our fine aggregate. So that is how the mix is self-compacting. And total volume 25% by the coarse aggregate content by volume. And you have to use both the stability and workability admissions. As I mentioned, powders are crucial. You need a more powder content, more paste content in self-compacting concrete when compared to the normal concrete. So if it has to maintain the homogeneity, and if it has to maintain the coarse aggregate in suspension, if it has to transport the coarse aggregate from one point where it poured to the other point, it should have a rich mortar. And this cohesiveness you can achieve due to large powder content. What you are adding, that means between 450 to 600 kgs. When you look into the IS 456, cement, restriction is that, right? 450 kg per cubic meter. If you're using only cement, you end up in heat of hydration, drying shrinkage, and other problems. So what are the various other materials? So we have to look for other alternatives. Which are the other materials? So these are the other materials, what we call supplementary cementitious materials. So you have fly ash, majorly we are using GBS, metakaolin, microsilica, alcofines, isocash. IS permits, IS 456 permits as per class 5. What it does by adding these supplementary cementitious materials, what exactly the reaction that happens? When you add the water to the cement, ordinary Portland cement, we all know hydration process happen. The final end product, what we call is calcium silicate hydrates. After the reaction, slowly it happens and the CSI gels keeps forming. Along with that, there is an excess calcium hydroxide line that is present in the mix. When you add the supplementary cementitious material, either fly ash, GBS, or metakaolin or silica fume, these supplementary cementitious materials react with whatever excess line is there and further react. That means what we call secondary reaction happens and forms further calcium silicate hydrates, CSH gels, which is the main part of the the concrete, or which gives the strength to the concrete. So by placing or by adding supplementary cementitious materials in a mix, instead of 100 CSH gels, you get 120 CSH gels, it will form. That means more gels will form, so that the more dense the concrete is, more strength you get, more durability. Strength and durability is different, but when you have more gels that forms, the concrete is more durable. Anyway, this is what the hydration process, silica, calcium hydroxide, CSH gel, it forms. There are other. And also, by adding pozzolan, it will increase strength, and also it increases the impermeability. What I mean to say, in the first case and second case, you can see the pictures. There are like the yellow color is the voids, if you say. In case of the second picture, which is containing pozzolan, having less void, that if you see the gray color. And also, by adding pozzolanas, the bleed pockets will get reduced and you get a dense hydrated piece, which by testing, you will get an increased compressive and tensile strength. So coming to another important part of my presentation, that is a fresh properties, very, very important. General normal concrete, what we do, we make the mix and then we place it in slump cone, Abraham's cone, lift it, check the vertical slump, or sometimes you do VB meter test, or sometimes the other test, very few tests, but most common is the slump cone. But in SCC, to know its stability, its filling ability, and passing ability, because you are placing, it has to fill the formwork at the same time, it has to pass through the reinforcement at the same time, it has to have the homogeneity throughout its movement. So you need to test the fresh properties thoroughly. So you have to simulate the field performance. So these are the three properties you have to test. One is the ability to flow into fill completely all spaces within formwork. Particularly, it has to go on its own weight. That means under gravity. Passing ability is, while passing through reinforcement between steel reinforcing bars, it should not get blocked, it should not get segregated. That is the property of the SCC. And another last thing is segregation resistance. Throughout the placing, transport, it should remain homogeneous. Okay, so you have to check that properties also. So these are the three properties, very, very important. Some of the test methods, so how do you check all these three properties? So these are the tests. I'll explain you one by one quickly. Slump flow, Jaring, Vfunnel, L-box, U-box, fill box, and GTM screen stability test. These are the tests which will give you the property of passing, filling, and segregation resistant properties. Start with slump flow. We know the regular up-down cone, 300 height, 100, 200 top and bottom dia. It's the most popular method. We generally measure for normal concrete vertical slump. But in case of SCC, you measure the horizontal slump, which measures the filling ability. When you place the concrete, lift the slump cone, it spreads. You measure the horizontal flow. Generally, it is between 500 to 800 mm, the recommended values. This is how, you pour the concrete in the slump cone, lift the concrete, it spreads, and then you measure the horizontal. This is how you will measure it. The spread. And there is also one more measurement, what we call T50 centimeter measure. What does that mean? When you place the concrete in the slump cone, when you lift it, the concrete will flow. The time taken to reach the 50 centimeter circle or 500 mm spread, how much time it will take, that you measure, it should be generally between 2 to 5 seconds. Let us watch a video. So he placed the self-compacting concrete in the slump cone, and he just cleared all that and he lifted it. So once it is not like normal concrete, it spreads. So what you have to take? You have to take the average of two measurements. Orthogonal direction, you will take the measurements. You take the average reading as the slump flow. Coming to the code book, if you look into the new IS 10262, there is a mention about self-compacting concrete. That is 2009 it is released. Sorry, 19. And then you can see the slump flow values of self-compacting concrete. They were divided into Indian Standard Code, divided into three categories: SF1, SF2, SF3. Flow between 550 to 650, which is appropriate for unreinforced or lightly reinforced structures, the tunneling linings and other jobs. And slump flow, which is more like 660 to 750, suitable for walls, columns, and other things, and 760 and above to up to 850. Heavy reinforced structures. This is what IS mentions about the slump flow. Coming to the next test, that is Vfunnel test, we assess the flowability of the fresh concrete. I don't know how many of you have properly followed the chemistry. When you check the viscosity of the resin or viscosity of the flow, we flow through a Vfunnel and it flows through a small orifice. Time taken to flow through the small orifice, we measure it, which gives you the flowability or viscosity of the resin or whatever. So similar test, this is the Vfunnel Dimensions. The time taken for concrete to flow through this narrow end, you will measure it. Recommended values are between 8 to 12 seconds. This is the first Vfunnel I have fabricated in 2001 using perplex sheet, and then because I wanted to see how the concrete it flows, and I would because see through. That's why I used the perplex sheets. And later in 2002, using at BMS College of Engineering. So this is the Vfunnel. Next measure using the same Vfunnel, we call it as a Vflow time for after 5 minutes. What does that mean? You will place the concrete, you will measure the time taken to flow through Vfunnel. That is the 0 minutes immediately after placing the concrete. This is in the second case, what you do, you place the concrete, you fill the Vfunnel with the concrete,